Good morning, everyone. This is Anders Oldebeck from Radiocrafts. I'm happy to host this event today. We want to talk about the wireless sensor networks and the wireless sensor modules. We had some issues with the seminar or the webinar this morning because of technology and the new GDPR, the Data Protection Act. That I'm sure you're aware of. There was an update on the software that we understood fairly late in the process. So I'm glad that some people has managed to get through that, and we will. And I also apologize for the inconvenience that you might have had. We will record this webinar, so if any of your colleagues were not able to make it, you can advise them to come to our website and download the webinar, where we will also send out an email with those details. But without further ado, let's get into this. So today, Frode Eskelund is going to talk about the most recent products we have released, which are the wireless sensor network modules that will help you and support in terms of building a very efficiently wireless sensor networks. I'm Anders Oldebeck, as I said, Sales and Marketing Director of Radiocraft. A couple of housekeeping items. We will have a 30 minutes webinar this morning planned. 10-15 minutes after that, we will have Q&A. Please also introduce yourself in the chat window so we know who is on the call. That's highly appreciated. If you have any questions during the webinar on really any topic, please put them in the chat window as well. We will summarize at the end of the presentation and go through them and respond to them to the best of our competence. And if anything still remains, we will then get back to you over email or some other way. The recorded version, as I said, will be posted on the webinar about a week after the webinar, if you want to go back to see it again, or if you want to share it with some of your colleagues or friends. And at the end, there will be a offer for a development kit during the Q&A session at the webinar as well. So let's get into the core of this. So what is a wireless sensor network node? This is what we're targeting with these products and how that fits, which will fit nicely into a wireless sensor network. So it has a sensor, a microcontroller, and an RF module. So next, please. So click. So what is then the reason for the pre-programmed sensor interface modules which we have created? It's a simple answer to that one. It's that we want to remove the microcontroller from the sensor node. And the reason for that is, as I'm sure you well understand, is to reduce the cost of the module, reduce the power dissipation or power consumption of the module, and allow for faster design time. So this is the background of what we'll talk about. If you click next. So the two systems that we have targeted for this is one is the wireless M-Bus system, where we will support a system which consists of a sensor node with this MSM module, as it's called, over the wireless M-Bus network into a gateway where our standard M-Bus module acts as the gateway module, and then you can get on to a WAN or LAN. The other system that we will support is the Sigfox system, where with our module, basically that is the complete sensor node together with some sensors, and then you get full access to internet over a Sigfox network. So this is just to frame the issue. I'll leave the floor to Frode with this and let him dive into the details.
Okay, thank you, Anders. Yes, I'm going to go through a little bit more in detail how these modules actually work. So I'm going to start off with just a brief description on what they actually are. Then we're going to go through the sensor types that we are supporting. We are going to go through how to set up this on a PCB. And also, I'm going to introduce you to an example system, which is basically a board that we developed here. Also, of course, we'll go through the configuration, both of the module and the sensor themselves, which will be quite interesting. And we will end with what kind of data is actually generated with these modules. And we will finish off, of course, with the Q&A. So to start off, what is these modules? Well, they are modules that contains both a radio and the sensor interfaces. So basically, they are standard Radiocrafts modules with additional sensor driver firmware on board, so you get a monolithic solution. They are easily configurable. You don't need to do any programming at all, only configuration. They use the UART interface for configuration, and that's just like all the other modules from Radiocrafts. You don't really need any external components except for the antenna and the sensors, and of course you will need power. Also, they are CE certified for the EU frequencies, and they are pre-assessed for FCC for the one module that we have, which is for that area in the world. We have these in two flavors, as Anders mentioned. We have one using the Sigfox network for data transfer. There we have one for the EU market and one for the FCC and ACMA markets. We also have two modules for the M-Bus protocol, which is both for the EU market, 868 megahertz, and one for the 169 megahertz. So what kind of sensors are we supporting? Well, this is the list, and if we start at the top, we have the Texas Instruments HGC 2010, which is an environmental sensor. It's capable of measuring temperature and humidity, and it's connected through the I2C bus. We also support the Sensirion SHT35, which is widely used in industry. It's a little bit more high performance than the HGC 2010 and a little bit more expensive. And it also connects to the I2C bus. We support one accelerometer. It's a 3-axis accelerometer. It's the LIST3DE from ST. It's connected to the SPI bus. Also, internally on the module, we have an analog to digital converter, and this has 3 channels. One is for the internal temperature of the module. The second one is for measuring the supply voltage directly into the module. So if your module or system is connected directly to a battery, then you can measure the battery voltage directly. Also, we have one pin that is connected directly to the ADC, where you can apply any voltage between 0 and 1.25 volts. So there you just measure the volts, and you can connect whatever you would like of analog sensors to that. For instance, a light sensor, a temperature sensor, or whatever you would prefer. Also on the module, we have 4 GPIOs, and the GPIOs is a little bit special because they can be used as actuators, so they can be configured as input or as output. So they can be used to drive LEDs or MOSFETs or whatever digital interface that you might have, and also to read digital inputs like Hall effects or buttons that is on the board. So what we've done is we have taken the standard module that we have and added the I2C, SPI, GPIOs, and an analog input, as you can see on this picture here. What we try to do is to cluster them together so that the routing on the PCB should be as easy as possible. Also, across all the modules, both the SSM and the MSM modules, we use the same footprint and also the same sensor connections. So the pin numbers are the same, so they are interchangeable. So you can use the same footprint for all your designs. In addition to the sensor interface, as you can see on the picture here, you have a UART interface and also reset if you would like to use that. So for a couple of examples how to connect this, it's really easy. For the I2C sensors, you have both for the HTC 2010 and the SHT35. The only thing that you really need is the sensor itself. You will just connect the I2C bus directly to the module. On some modules, you would need an external pull-up resistor on the lines, which typically is 4.7 kilo ohms. It's what is more or less always used on low-speed I2C buses. So that's really it. For the SPI, it's kind of the same. You just connect one-to-one, the clock and multimeter and chip select, and the driver and everything in the module fixes everything else. For the GPIO, it would be depend on what you connect to it. So for an example, here we have the Hall detector, the SL353LT, which is also present on the sensor board, which has its output just connected directly to the GPIO. So the Hall out on this figure is just connected to the GPIO, which is configured as an input, and that is all you really need. So, as our example system, we have the Radiocrafts sensor board. This is a board that we developed here. It contains everything that you need to test and develop all things you would like to do. It contains the power section, of course, with everything to power all the sensors and the module. It got USB to PC connector, which basically gives you a virtual COM port for configuration. It contains all the sensors, of course, on the same board, and it also has all the IOs on the module routed out to the sides to some connector holes, which enables you to connect whatever you would like to test onto the board or use it as pins for measuring. The block diagram for the sensor board looks like this, and for this presentation, the most interesting things are on the right side. So here you can see, for instance, that the Hall sensor is connected to I/O. The SPI bus is connected to the accelerometer, and for the analog input, you can see that we have connected a light sensor. So it detects the intensity of the light and converts it to a voltage, which is then fed into the analog input of the module. That enables you to test that general analog input in a fun way. So how do you configure the module? Well, it's done with just the same way as with any other module from Radiocrafts. It uses the UART, as I previously mentioned, and that means that you can use your own tool if you want to develop anything, or you can use any terminal that you would like, or you can use our CCT tool, which is downloadable from our website. That gives you a few additional things, like a list of all the registers that you can modify, for instance. A list of all the configuration commands can be found in the user manuals. It would be a little bit too detailed for this presentation, but the user manuals are on the website, so you can just download them and you can have a look at what is supported. There is, however, one command that we are going to go through in a little bit more detail here, and that is for configuring the sensors themselves. The configuration of sensors is done in configuration mode, just like all other configuration. We have implemented a new command, which is capital J. The capital J command is followed by a configuration array consisting of exactly 101 byte values. These describe all the sensors and all the parameters. There is no limit on the order of sensors. It's not important. The only thing is that you would need to start the first byte with configuration, and all configurations of other sensor will have to be back to back. The last byte will have to be a 0, which is just to check that what is sent is more or less sane. So for the example that you see here, we have the black values. They are configuring one sensor. The green values are configuring another sensor. And all the red zeros are just padding. You have to send 101 bytes exactly after the J command. So if you have a spare, then you will just have to pad in zeros. All the details on all bits and bytes and everything is in the user manual. But this can, of course, be a little bit tedious to do. So what we also done is we have created a configuration tool that eases this configuration part, and this should make it really easy to configure the sensors. So what you start off with is an input file. So we write an input file like this. This is a complete file for setting up the HTC 2010. It's just a regular text file. It's written in the JSON format, which is quite human readable. So for this example, we are configuring the HTC 2010 with a sampling rate of sampling every 20 seconds, for instance. I'm going to go through all the different parameters a little bit later. When you have created your file, you will run the configuration tool. And during the runtime, you will have a dump quite like this. So it just lists all the sensor configurations one by one. So as you can see here, the HTC 2010 first, and the ADC, and so forth. And it ends with a final full configuration array, which is all the 101 bytes. So this is good for checking the details of everything if you want to do that. But also we create a text file which contains only the configuration string, the full configuration string, 101 bytes, and it's also stored in a regular text file just like this. So what you can do with that is, yeah, it's of course stored, so you don't have to look at the output of the program in itself. And you can use this to parse by your own programs, or you can just use copy paste. And one thing that you can easily do is if you're using our CCT tool, you start up the CCT tool, you enter config mode, and you send the J command, and then you just copy paste this, and you exit config mode, and all the sensors are configured. So it's really that easy. So for the configuration details, well, we have some basic parameters which is common for most sensors, and these are the type, version, and period. The type is, of course, what kind of sensor are you going to configure? And that could be the HTC 2010, the SHC 35, or whatever on that list. We have a version number, which is now only 1, and it's there because of possible future backwards compatibility. So if you ever make a version 2 or something, then it will be backwards compatible. The period is the interval between sampling values and waking up the sensor. And of course, for low power designs, you want to have this as large as possible. But of course, if you want some better response time, then you can lower this. So for example, if you want to enable sensor HTC 2010 and sample it every 20 seconds, this is the way to do it. In the input file, the JSON file, as I previously mentioned, you set the type to HTC 2010. You set the version to 1, which is the only legal value now, and you set the period to 20, which means 20 seconds. The GPIO parameters are maybe the most advanced. Here you can set the GPIO direction to input or to output. You have something called an initial state, which is which level the I/O is to be in when the module resets. You have the initial delay, which says how long will the initial state be there. And then you have a low time and high time, which will give you the duty cycle of the GPIO. So it will cycle forever according to those values. So for an example, you can have a look at the figure in the bottom here. Here you set the GPIO to low after a reset. That is the first initial state. It's also configured as an output, of course. Then you will wait 5 seconds after the reset, and then it will start toggling between low and high for 1 second each. So we will stay low for 1 second and high for 1 second. If you for some reason didn't want to have low at all, you could just set it to 0, and then it would be after 5 seconds, it would just go high and stay there. We also implemented some triggers. So what these basically does is that if you have some condition, then you will send a transmission of a packet. It's usually you will set up a regular transmission, so every minute or every hour or something, then you send the packet. But you can also send a packet given some conditions. So this is given with a threshold operator and 2 parameters. So the first, the operator is could be greater than, less than, equal to, or maybe a change. The first parameter is which sensor channel to use. So for instance, for the environmental sensors, you can select between temperature and humidity. And the second parameter is the limit value itself. So here you have an example in the bottom here, which sets a trigger when the temperature is greater than 30 degrees C for the HDC 2010. And how you would do that is just to set the threshold operator to greater than. You will set the threshold parameter 1 to 1, which means the temperature. And you would set the second parameter to the actual degrees C. You don't need any conversion or anything. 30 means 30 degrees C. We also have implemented some very basic digital signal processing capabilities. It's just like for the threshold operators, you have a DSP operator, which can be averaging or keep the max and min values. The first parameter is just as in the previous slide, it selects the sensor channel. And the second parameter is not really used. So for the example here, we are using averaging on the Z axis of the accelerometer. So then you set the DSP operator to averaging. The first parameter is 4, which corresponds to the Z axis. And the second parameter, as long as it's not used, is just set to 0. So when everything is configured and you're happy, you would expect some data. And this will differ between the SSM and the MSM, of course, because they are 2 completely different protocols. For the Sigfox, you have a limitation on 12 bytes on the payload. So that means that all data is very compact. However, all the values are in sane values, you can say, or sane types. So you don't need really any conversion on them. That is already done in the module. So for example, if you have configured the module to read the ADC and have connected the SST35, you will have these 6 bytes in the payload. First, the analog input, which is the value given in 100s of volts. Second byte is the internal module temperature, that's given in whole degrees centigrade. The third byte is module supply voltage, which is given in tens of volts. And the fourth and fifth bytes are the temperature of the SST35. It's as it's a precision temperature measurement sensor, so we would need 16 bytes. So we need to concatenate these 2 bytes, and then it will get the degrees in tens of degrees C. It's also, of course, supporting both positive and negative temperatures. And the final byte would be just the relative humidity given in whole percent. So that value will be between 0 and 100. For the MSM, it's quite different, of course, but the data that we are sending out, that conforms to the M-Bus standard values. So everything except for the accelerometer, actually, because there are no G definitions in the M-Bus standard, are sent on the value types that are described in the standard. So for the same example, you will have an M-Bus payload, which is shown here. You see the bold white, these are for the ADC, and the bold yellow is for the SHT-35. I'm not going to go through all the details here. That would be a little bit too much, but we can take, for instance, the temperature of the SHT-35. Here you see that in the second to last bullet point here, you have the diff of 0.2, which means that, okay, you are sending a 16-bit integer. You have a diff of 66, which means external temperature, and 10 to the minus 1 degrees C. And the data is 1301. So what that means is you have a temperature of 27.5 degrees centigrade. So that was my presentation on all the details. It was a little bit quick, but then you have an overview of what this thing can do, and the takeaway is how easy it is to actually have a system up and running and working without any programming or much effort. So if you have any questions, please put them in the chat, and we will try to answer them as good as we can. Thank you.
Thank you, Frode. Appreciate that. That was a good, fairly technical description of what we've done here in terms of trying to simplify the design of wireless sensor networks, where we now have created those autonomous modules that can actually then interface directly to sensors with basically nothing else than a battery and an antenna to support that. We're waiting for questions in the chat window if there are any. There is one thing that might be of interest, and that is, if a customer would like to add another sensor type, one that is not predefined in the modules as it is today, how can we support that, Frode?
Yes, that is that we can support, but it will depend on the case. So we will have to do that case by case. What we've done is it's really easy to create new drivers. The framework is quite flexible. So if we have some customers that wants to do that, then they can just contact us, and we can see what we can do. Probably we could do that. So.
Okay, yeah, thanks. So we will take in anything. I have a question for Gareth here. Pricing on these modules for 10K, it depends, I should say, on the system, and there's 4 modules here. It's 2 different wireless M-Bus and 2 different on the Sigfox. They are priced in the same level as our regular modules, so which means that we're talking about, for the regular modules, in the $10 range, and the wireless 169 megahertz a little bit higher. From Fari, question is, the sensor board that you have described, is that already a product? If so, how would it be possible to try different modules? It is a product. We sell that as part of our development kits for these modules, but they are pre-populated with the module that you then describe when ordering. So there is, for example, one development kit for the RC1701. HP does MSM, which is then populated with that particular module, and similarly for the Sigfox modules, etc. So you cannot change unless you have very, very skilled operator to desolder and resolder something, but I would not recommend that. Yeah, if there's anything else there, the other thing I just wanted to highlight here, which maybe didn't come through in the presentation that much, is that if you use the 169 megahertz version of the wireless M-Bus, you get a low power WAN network with more than kilometer range in sort of normal conditions by using the 169 megahertz wireless M-Bus module MSM together with our standard wireless M-Bus module as well on the gateway side. And that is basically the complete low power WAN system that you get with more than a kilometer range in practical condition, which then is a much cheaper and competitive to a system like LoRa, for example. Fari came back with another one. Are the wireless M-Bus modules different from RC1701HP and RC1180? I might have missed the codes for those modules yet. So if I try to understand the question here, so these modules that have the integrated sensor interface, they have the ending called MSM. So RC1701 HP-MSM, which is then not the same as the RC1701 HP-M-Bus 4, which is the standard module. If this is the good response to the question, if I understood that right. Gareth, would this temp sensor work with Scilab's drop-in product to the Sensorion? I cannot answer that. We support the Sensorion product here. If it's drop-in replacement, I guess it would work, but I have no guarantees on that. Frode, do you know anything about that one? It's more technical than I can respond to.
Not with that particular IC, no. But it depends on how drop-in compliant it actually is. So yeah, if it's the same registers and the same interface, it should work, I guess. But I'm not been able to look into that exact IC, no.
Okay. Gareth, LoRa, any products for the future? We have not decided to go ahead with LoRa for the time being. We have decided to, for the short term, go another route, which you will see us announcing now during next month, which is June. We will have that on display at the Sensor and Test in Nuremberg. It is a system based on 802.15.4 G and E. It does not have the same range, but it has much higher reliability than LoRa, which we actually believe is more adequate for the industrial market where we are normally operating. We don't focus on range 100%, but we have long range. But in addition to the long range, we have very, very good reliability. But stay tuned for that. There will be announcements coming out here in the next few weeks. If there are any more questions, we're happy to respond to those. We'll stay on here for another couple of minutes. If not, I do want to thank the people that came through, even though we had some, as I said, some issues with the Data Protection Act here that is worked against us for a little bit. So my apologies again for that. We will send out we will post the seminar on our website as always, and send out the information for that. So with that, Frode, any final words from you?
We got another question actually.
Oh, sorry.
Yeah.
Neil, can you work with I2C sensors not mentioned here? And I guess, Frode, this is your question.
Yeah. Yes, we can do that, but that would depend on that. Then we would have to write another driver for it. So if you have some sensor that you want us to develop a driver for, you can just contact sales, I guess. So we can have a look at that. But that would be on a case-by-case basis.
Yeah. So please contact sales at Radiocrafts the email address, and we will look at it and respond to it. But it will be a factory upgrade of the module with the new version of the firmware.